Okay, hi, this is Elliot Fishman, and welcome to our latest podcast. And I wish everybody a belated 4th of July. Well, it's not belated, but it's over. And some of you are probably back at work, first week of the year, and welcome back. So I think I put down that this week would be principles of deep learning. So we're going to go through some of that, and I thought perhaps just a couple things in advance. You can see how deep learning or artificial intelligence, whatever you want to call it these days, is really becoming very big in radiology. Obviously, you read articles, and it's not just radiology. There's an article today about how they developed these deep learning algorithms to be able to pick up retina degeneration earlier than an ophthalmologist can. So there's, whether it's dermatology or ophthalmology, radiology, pathology, you name the field, cardiology. But radiology, Dave Blumke is the new editor of radiology. You can see I'm picking up these papers. It was announced today, which we knew was just a matter of formality, that radiology, artificial intelligence, is seeking initial research. So radiology is going to have 3 new magazines. One is on, they'll all be online. One is on cardiovascular. I forgot what the second one is, but the third one's artificial intelligence, which you'll see, I think, in January 2019. So it does make the point that even radiology, it's not just they're sticking some articles in radiology with the other 30 articles a month, but within 6 months, there will be a journal within radiology that's totally radiology. So that indeed is pretty impressive, and it shows where things are going. I was away this past weekend, and one of the things that we had to do, one of the exercises, was this, where everyone had to give a TED Talk. And it was really, you sat there, and it was like in front of 20, maybe not 20 people, but 18 people, and you gave a TED Talk. And you could do it on anything you wanted, anything for 3 to 5 minutes. It really was interesting because what people pick up on, or what they do may relate to their life. Some people spoke about something that happened when they were a child that impacted their entire life. Some people spoke about happy times. Some people spoke about sad times. Some people spoke about their practice. Some people spoke about flying, about joy, happiness. So there was no right answer. It was whatever you want to speak about. It was really terrific. I went first, so I really couldn't, I don't know where to start from, but I spoke about the comment maybe we made before about deep learning, that people writing a lot of articles and it says man against machine. And I think the point I made and the point we commented on before is that that's kind of sort of dumb in the sense that it's to be successful as man with machine. The truth is, if it's man versus machine, you're probably going to lose. Let's be honest. We talk about many different things where you could be the best mathematician. You could add, subtract, multiply, divide. You'd be incredible, but you got a cell phone, you type it in. A 5-year-old is Einstein. So if you really want to do well, I think if we really want to do well, and this is the message for radiology, of course, is that it's not going to be us versus the machine. I don't see the machines replacing us, maybe not for a while, surely. But to succeed, I think you're going to have to be using artificial intelligence. I think if you're not using artificial intelligence, and maybe it's not next year, maybe it's 3 years, 2 years, 5 years, whatever it is, if you're not using artificial intelligence in your practice, you're not going to have a practice, because it's not going to be so much do you use it or not. It's going to be something that we routinely use that enhances our ability to make the right diagnosis. Remember, I spoke to you about the Felix Project, about how we're trying to detect pancreatic cancer early, and we're doing a great job. And it's important to recognize that the goal of the Felix Project is not going to be to replace the radiologist, but that when you sit down to read the films, the pancreas will have been read saying you, hey, look here, there's something funny. And if we get better than that, we'd say, okay, not only is something funny, but it's an adenocarcinoma, or it's an IPMN, or serous cyst adenoma, or MCN, whatever you want to call it, it'll be there. But I think it's this ability to enhance our capabilities. And in a field where people say that 30% misdiagnosis, particularly when there's a finding present, when half the misses essentially are something misinterpreted and half the misses are something which is not seen, we need to do better, and that's where deep learning will help us. Now, fast forward, and if you have any questions, it's a good time, or over the next few minutes to ask questions. And we'll say hello to Alberta in Hawaii. But there's a good article that's worthwhile reading. It's in Radiology. It's by Gary Choi. And it's last month, or actually it's not even, it came out in the last month electronically. The journal is not yet published that it's going to be in, so maybe 3 months off. And it spoke about many things that perhaps are worthwhile looking at and understanding. So some of the things, and on CTSS, remember we have this Pearl section. We now have a specific deep learning section in Pearls, and so we're going to put all the Pearls there. We are building on CTSS a section on deep learning. We're going to have lectures. There's 2 lectures coming up very soon from Karen Horton, for example. We're going to try to work with NVIDIA to put more lectures, content up, information to help you understand things, help all of us understand things better. And this article spoke about the machine learning tasks are typically classified into 3 broad categories, depending on the task: supervised, unsupervised, reinforced learning. So the way you like to think about it is, it'd be wonderful if things were unsupervised. That would basically mean you took a whole bunch of CT scans, threw them in the computer learned everything. But as we learned from doing the pancreas, we use supervised data. So the way we trained the pancreas, the computer for the pancreas, we took well over 1,000 normals, annotated everything in the abdomen from liver, spleen, kidneys, bowel, SMA, SMB, you name it. Taught that to the computer, and then when the computer was good at recognizing organs, we then started teaching the computer what a tumor looks like. And so it's really, that was supervised learning. And supervised learning is, and from this article says it nicely, data labels are provided to the algorithm in the training phase. There is supervision and training. The expected outputs are usually labeled by human experts and serve as ground truth. The goal of the algorithm is usually to learn a general rule that maps inputs to outputs. And in machine learning, ground truth refers to the data assumed to be true. So again, one of the things to remember is, as you're doing the training, that you need truth. So that's why we have experts labeling. You don't have a bunch of first-year med students who don't know anything, perhaps, but you need to have expertise. We have people who are experts, and then another expert, one of myself, Satomi, Linda Chu, will check it, because whatever you teach the computer, if you teach the computer the wrong things, the computer's going to behave poorly. So you need to make sure you have ground truth that is really indeed the truth. And this idea about supervised data becomes very critical. I think in some fields, you can get away with it. This quote, in unsupervised learning, no data labels are given to the learning algorithm. The goal of this machine learning task is to find the hidden structures in the data and to separate data into clusters or groups. In reinforced learning, a computer program performs a certain task in a dynamic environment, which it receives feedback in terms of positive and negative reinforcement. Reinforcement learning is learning from the consequences of interactions with the environment without being explicitly taught. And perhaps one way of thinking about that would have been, if you were trying to teach the computer to play chess, that you would play against it and it would learn the good and the bad moves and then get better. It would also learn all of the other games that were ever played and see by example what the things are to do when you move the rook, when you move any of the pieces, when you move the queen, when you castle, and the like. So it's really this unsupervised learning works in some things, and perhaps, they taught computers to recognize dogs. You showed a lot of dogs, then it recognizes a dog. People make the point, Alan Yulee makes the point, that if a dog wearing a tuxedo, it's not going to recognize the dog. However, if you take a 2-year-old and you put a tuxedo on a dog, it's going to say doggy. And if the dog is wearing a ski mask, it's going to say dog. So I think computers really do well with supervised learning. The challenge with supervised learning is we spend months and years developing the right data sets. It's expensive, it's time consuming, and the like. This article also makes the point that the collecting high quality ground truth data, development of generalizable and diagnostic accurate techniques, and workflow integration are key challenges for the creation and adoption of machine learning in radiology practice. And I think that becomes so very important for us to recognize that we really need to create this data sets. And the question would be, is there some way of people cooperating? I think the biggest challenge when you look at Google and IBM, Watson, whatever, NVIDIA, is they need data. And simply getting data that's just a bunch of things that are in someone's computer or in someone's PAC system is really not going to do it. So it's really the supervised data that becomes very, very important. Now, this article also says, and I'll give you a quote, in general, machine learning techniques are developed by using a training test system. These sets of data for training and validation are needed. And during training, the algorithm learns from examples. The validation set is used to evaluate different model fits on a separate data and to tune the parameters. So one of the things we do learn is that we then test the computer, we teach the computer, we challenge the computer, we look at errors, and then we develop ways of helping the computer not make errors. It's very much ourselves. When we learn radiology, you learn certain rules, you don't learn everything. You missed an elbow fracture, you learn to look at the fat pad. Computer equivalent, you teach it to look at the fat pad. You teach it to look at things. This idea about machine learning, but of course the good thing is once the machine learns, it can learn from infinite examples. You could look at hundreds and thousands of cases perhaps. The machine can look at millions of cases. So if the machine can get all of those information, remember I think I mentioned previously that machine learning can look at skin lesions and say benign malignant. And where the best dermatologists have seen thousands and thousands of cases, the machine looked at 1.2 million. So the sheer numbers give a certain advantage to machine. A good quote from the article, fundamentally, machine learning is powerful because it is not brittle. A rule-based approach may break when exposed to the real world because the real world often has examples that are not captured within the rules that programmer uses to do the algorithm. With machine learning, the system simply does statistical approximation to respond most approximately based on its learning set, which means it's flexible. Additionally, machine learning is a powerful tool because it is generic. That is the same concept that I've used for self-driving cars, I use for medical imaging. Generalizable with machine learning allows for rapid expansion into different fields, including medicine. So when we speak with NVIDIA, they will talk about their expertise at this point is not a whole lot of medicine, though they're getting there, but their expertise is driverless cars. Their expertise is mobile devices. They have lots of expertise, and you can take the expertise from one domain and move it into the other domain. A key reason for collaboration is taking expertise in other domains and move it into radiology. One of the things, of course, we don't want to do is rediscover the wheel. So since we're in a rush, we should be in a rush because patients' lives are at stake, since we're in a rush to develop the algorithms as quickly as possible, we try to take as much information and as much knowledge from other domains. Alan Yulee, who's in charge of the computer graphics side of what we do in computer vision, has 30 years of expertise in computers. So what he learned from looking at dog, cat, all those things, and everything else he's done, he then can apply into medicine. So I think one of the exciting things about medicine and why we may benefit is because the faster things go in other domains, the better self-driving cars work and how it recognizes information and changing models. That's only going to benefit radiology. I think there's another good quote. Machine learning approaches to the interrogation of a wide spectrum of data has the potential to further personalize healthcare far beyond what would be possible through imaging applications alone. And one of the things also at this point, and I use that quote to make the point that in deep learning, radiology is step one. We need to read the images. But then you need to build in the clinical history, the presentation. Based on imaging and presentation, appearance, then you need to build in how you manage the patient. Will we notice that a certain appearance, a certain lab value, will then mean patients respond or don't respond to a specific drug? That is going to happen. So I think not only will we do better in terms of the imaging, but we're going to be better in the big picture, which is the patient. So deep learning will not only affect and needs to affect not only radiology, but pathology, oncology, drug delivery, and drug development. So if you notice, everybody is impacted by deep learning, and that's why it's very exciting, and what the challenges are is a lot to do. So let's see. A couple questions here. Helping people is the objective, Javier says, and I 100% agree. And the reason we're trying to do things well is because we don't do things well, or as well as we could, despite our best efforts. Here's Sven says, AI is referred to in the context of computer indicating abnormalities, but how do you see the role of AI in the computer, presenting, acquiring data, and the like? I think you're 100% right. I think AI will impact everything we do, from how patients are scheduled, to how we put them on the scanner, to how the computer will determine what the best protocol is based on patient size. The AI will allow us to give the lowest radiation dose possible for that patient, understanding what we need to see and what the patient's size is. Computers now will get smarter, and they'll be built into the scanner. When you speak to NVIDIA, they talk about putting their chips in the scanner at the acquisition time. So it's at the acquisition that will improve things. You also will see how we read, how we interpret, how our reports are built, how we bill, where we put our scanners, what hours we're open, how we schedule patients. I think you're 100% right. Everything of what we do will be impacted by AI. It's going to change the hanging protocols. It's going to bring you information. I always like to think about it as an F-35. When you're a fighter pilot, you have split-second change, but all that information is coming to you. You're not asking for it. So if I'm looking at a real pancreatic mass, all the information that relates to the pancreas should come to me about that patient. Perhaps the staging system should come. Perhaps questions that I need to answer should come. And perhaps, things I don't think about should come. And if I don't mention the SMA, the computer should say, hey, Fishman, you didn't mention the SMA. Say something about it. So I think it is going to change. And I think over the coming year or years, we will have lectures, we'll have speakers, we'll have talks on CTisus, and we'll have discussions here on Facebook about really what does it take to do AI and how AI is impacting everything. So I think it's very exciting. I appreciate everybody's questions. And I guess my time is up. If you have any questions after you think of, write it down. I'll try to answer it. If not, have a great day and keep cool. See you later. Bye.